Hey there, in the previous video, I briefly introduced the concept of ETL, that is extraction, transformation and loading. In this particular section, we are going to go much deeper into ETL because it plays a massive role in successfully designing and building a data warehouse. We'll look at different ETL patterns and approaches that are commonly used in industry. We'll also spend a good amount of time on the T part of the ETL, that is transformation, because that is usually where most of the complexity comes in. You'll see different kinds of transformations that are commonly needed when preparing raw data for analytics and reporting. We'll also talk about a different approach called as ELT. In ELT, instead of transforming the data in the middle of the pipeline, we'll push those transformation toward the end of the workflow. This approach is extremely common in modern big data systems and data lakes. So with that foundation in place, let us jump in and start exploring ETL and its role in data warehousing. Let us now talk about ETL and also compare it with its close cousin ELT. In a typical data warehousing setup, we pull up the data from different source applications into a data warehouse or data mart using a process called as ETL. ETL stands for extract, transform and load. Let us look at extraction. That is the first step. It is all about pulling the data quickly from multiple source systems. Traditionally, this usually happens in batches, maybe every hour, every day, or sometimes every few minutes, depending on the business need. That is why ETL is generally considered a batch oriented process. When the data is extracted, it is usually brought into the data warehousing environment in its raw form that has errors, inconsistency and everything else. So instead of sending it directly to where business user access the reports and dashboards, the data first lands in a staging layer. From there comes the transformation phase. This is where we clean and standardize the data so we can make proper apples to apples comparison. For example, different systems may store customer or product information in completely different formats. One application may structure product IDs differently from another, or customer records may follow different rules across departments. During transformation, we prepare and normalize the data so everything becomes as consistent and uniform as possible before it reaches the user access layer. And honestly, transformation can get pretty complex. There are a lot of cleaning, validation, restructuring and integration tasks that are involved, and later on we'll look at some common transformations and you will almost certainly encounter in real world data warehousing projects. Once the transformations are complete, then the final step is the cleaning and the standardizing of the data into the user access layer, where it becomes available for business intelligence and analytics. Now, traditional ETL does come with some challenges. One major challenge is that a lot of business analysis and data modeling needs to happen upfront before the data is even stored. You cannot just dump the data from different systems into a warehouse and hope everything works. You need to understand the business rules, the design schema, and define how the data should be structured ahead of time. And that is where ELT started becoming popular, especially with the rise of big data and data lakes. With ELT, we simply flip the order. Instead of extraction, transform and load, we do extract, load and transform. So rather than transforming the data before storing it, we first load the data into a large scale storage environment and worry about transformation later on when we actually need them. In ELT environment, data is often pushed directly into platforms like Hadoop or HDFS or AWS S3 or other large-scale storage systems. Structured, semi-structured, and even unstructured data can all be stored as is without much concern about schema design upfront. The idea is simple, just store everything first and analyze later. This approach removes a lot of upfront data modeling effort. Instead of carefully preparing every piece of data before loading it, we defer that work until the data is actually needed for whatever the purpose is. Another advantage is obviously the performance. Traditional ETL often relies on separate ETL servers to kind of handle the transformation. In ELT, once the data is inside a big data platform, we can use the platform's distributed computing power to process huge volumes of data much more efficiently. You may also have heard of the terms like schema on write and schema on read. Schema on write is basically it's a traditional ETL approach. The structure of the data is defined before the data is stored. Schema on read, which is common in ELT, means we store the data first, and I mean raw data at first, and then define the structure later on when somebody actually wants to use or analyze data. So, in simple terms, traditional data warehousing usually follow ETL. Modern data lakes and big data platforms often prefer if ELT, and hybrid environments may use a kind of a combination of both depending on the use case. Now, ETL itself usually happens in two major forms. One is initial ETL, second one is incremental ETL. For now, we'll be focusing on the first one, that is the initial ETL, and I'll talk about incremental ETL later on. So, as the name suggests, initial ETL is typically something that you do only once, usually right before the data warehouse officially goes live. The goal here is to gather all the important data needed to launch the warehouse properly. So we extract the data from source system, move it into the staging layer, perform all the necessary transformation, and finally load it into the user access layer. Once that is done, the warehouse is basically ready for reporting, dashboards, analytics, and business intelligence activity. Now, technically, you can rerun an initial ETL later if needed. For example, maybe the warehouse becomes corrupted, maybe there's a major platform migration, or maybe the environment has to be rebuilt from the scratch. In situations like that, you might perform the initial ETL process again, but under normal circumstances it generally is a one time setup activity, not something that runs regularly. One really important concept here, however, is relevance. In a traditional data warehousing environment, we do not bring in every single piece of data from every source system. That is more common in big data or data lake environments, where you can basically dump massive volumes of raw data into storage and figure things out later on. But in a traditional in a traditional warehousing, the storage and the modeling and the performance are more carefully managed. So instead of loading everything, we focus on loading the relevant data only. In other words, we bring in the data that we know will absolutely be required for BI or analytics. For example, if the business already knows it needs certain reports, dashboards, or visualization, then the underlying data supporting those use cases definitely need to be included during the initial ETL. At the same time, we also usually include data that will probably become useful soon. Maybe the business plans to expand into predictive analytics or data mining or more advanced reporting later on. There may be closely related datasets that are not needed on day one, but there's a strong chance that they will become important shortly after the launch. So in practice, initial ETL often includes both data that is definitely needed and data that is likely to be needed soon. Another major part of initial ETL is historical data. Remember, when a brand new data warehouse is first created, it has no history inside it. But many BI and analytics use cases rely heavily on historical trends, things like year over year comparison or month over month comparison, sales growth patterns, or customer behavior over time, or forecasting or trend analysis, and so on and so forth. So during the initial ETL, the organizations often load months or even years of historical data into the warehouse right from the beginning. That way, the moment the warehouse goes live, users can immediately start analyzing trends instead of waiting months for data to accumulate. And once the initial ETL is complete, the warehouse is officially up and running. From that point onwards, the focus shifts to keeping the warehouse continuously updated, and that is exactly where incremental ETL comes into the picture. Now, let us take a closer look at the other part, that is the incremental ETL. Initial ETL is generally one-time setup process that happens before the data warehouse goes live, and that is where we gather all the relevant historical and operational data needed to get the warehouse up and running for BI and analytics. And normally you will only redo that initial ETL in unusual situations, as I talked about before. Maybe the warehouse got corrupted or rebuilt or migration, whatever. Incremental ETL, on the other hand, something that happens continuously on a regular schedule. The whole purpose of incremental ETA is to keep the data warehouse fresh and up to date over time. As new data comes into the organization, we need to bring that into the warehouse as well. So maybe new customers are added, new employees joined, or new products got launched, or new students enrolled, or new faculty members are hired. All of that new information needs to be incrementally added into the warehouse. At the same time, we also need to handle modified data. For example, an employee got promoted, a product price changed, or a customer changed his or her address, or maybe a university updates the title of a course. Those updates needs to be reflected inside the data warehouse as well. And then there is deleted or inactive data. But here's something important in data warehousing: deleting data does not usually mean physically removing it. For instance, a customer may cancel a subscription of Netflix, a student may leave the university, or an employee may resign. So in those operational system, those records might disappear or become inactive, but in a data warehouse, we usually keep that information or historical reporting and analytics. So instead of purging the data entirely, we often mark it as inactive or no longer currently needed or dormant, while still preserving the historical record itself. Now, the main goal of incremental ETL is to make sure that the warehouse stays reasonably current. Remember, one of the classic principles of data warehousing: the warehouse is considered non-volatile. That means that between ETL runs, the data generally stays stable and does not constantly change underneath analysts while they are doing the reporting or strategic analysis. This stability is useful, but the downside is that the data slowly becomes the stale between the updates. So incremental ETL is what periodically kind of refreshes the warehouse with the latest information from the source system. Now there are four incremental ETL patterns that you'll commonly hear about. First one is the append pattern. This is probably the simplest one to understand. Here you already have existing data in the warehouse and you simply add new rows on top of it. For example, if yesterday's sales data already exists, today's sales data just got appended to the table. You are basically growing the data warehouse over time by continuously adding new records. The second pattern is in place update pattern. In this case, you're not adding the new rows, you're only modifying the existing one. So imagine a table with like maybe 1000 records. After the ETL update, you'll still have 1000 records, but maybe a few rows now contain updated values. For example, an employee's designation changes, product price gets updated, or a customer's status changes. So the number of rows stays the same, but some column values get overwritten. Later, when we discuss dimensional modeling, we'll see how this connects to concepts like type 1 SCD, or slowly changing dimensions. Now the third pattern, however, is the complete replacement pattern, which is a bit more aggressive. So instead of updating only the changed row, we completely overwrite an entire section of the warehouse, even if most of the data has not actually changed. So maybe one small value is different, but the ETL process still reloads the full dataset or partition again from the scratch. This approach is simpler in some older architectures, but it is usually less efficient. And finally, we have the rolling append pattern. This pattern is used when the organization decides to maintain only a fixed amount of historical data. For example, the last 36 months of sales history or the last 10 years of employees record. Whenever new data is appended, the oldest equivalent data gets removed. So imagine you store exactly like maybe 104 weeks of sales data, that is 2 years. Each week you add the newest week and you remove the oldest week. The data thereby, or should I say, the data window keeps rolling forward over time. Now, historically, all the patterns have been used in data warehousing system, but in modern environment, especially newer architecture, most incremental ETL processes primarily use this two, that is the append pattern and in-place updates. Those approaches fit very naturally with the modern dimensional modeling techniques and tend to be much more efficient. You'll still occasionally encounter complete replacement or rolling append strategies, especially in older legacy data warehouses that have not been kind of re-architect in many years. But in most common modern systems today, append and in place update are by far the most common approaches. Now let us take a look at data transformation, which is one of the most important part of ETL process. Remember, ETL stands for extract, transform and load, and honestly this is the middle one, that is the transformation, is where a huge amount of real work happens when building a functional data warehouse. The transformation phase has two big overall goals. The first goal is uniformity. In real organization, data usually comes from multiple systems, applications or departments and platforms and so on. And even when those systems are storing the same kind of information, like students or customers or employees or faculty members or products or whatever, they often store that information in completely different manner. So one of the major jobs of transformation is making all of that data consistent. The whole idea is to create kind of apples to apples comparison, as I talked before, so that when users run the dashboards, reports or BI queries, the data behaves like it came from one cleaned unified system, even though underneath it may have come from dozens of different sources. The second goal of transformation is restructuring the data. Think about what happens during extraction. We basically pull large amount of relatively raw data into the staging layer. At that point, the data can be messy, inconsistent or incomplete or unorganized across various systems. So transformation is where we reorganize and reshape all that raw information into a clean, well-designed structure that fits the architect of the data warehouse. You can almost picture it like this. Extraction pulls the data, transformation throws everything up in the air and then reorganize it neatly into a highly engineered, structured, optimized way for analytics and other purposes. Now there are several common transformation techniques used in ETL. I'll focus on few major ones. The first transformation type is data value unification, and I'll use an example with a university that has two campuses, right? Campus 1 and campus 2, each running its own software system. Suppose both systems or both campuses are hiring new faculty members. Campus 1 stored faculty ranks like professor and assistant professor and lecturer. Maybe some are fully spelled out and some are abbreviated. But Campus 2 uses a totally different representation. For example, P stands for professor, AP stands for assistant professor, L stands for lecturer. Now technically both these systems mean the same thing. They are representing the same thing, but from a reporting and analytics perspective, this inconsistency becomes a problem. Remember, business users should not have to care about the data, or should I say where the data is coming from or how different source system represent things internally. They just want clean, easy to use data. So during transformation, we have to standardize this value into one common representation. Maybe we decide the warehouse will always use the campus 2, abbreviation like P, AP, and L. So even if campus 1 originally stored this as professor in full text, by the time the data reaches the warehouse, it gets transformed into a standardized version, and that process is called data value unification. Now, something very similar but slightly different is called as data type and size unification. Here, the issue is not the actual value. The issue is how the data fields themselves are defined. For example, campus 1 may define last name as 35 character, and campus 2 may define it as 30 character. Similarly, first name in campus 1 would be 20 character, in campus 2 that would be 25, and maybe rank codes are having this similar problem as well. Now obviously we don't want users dealing with multiple versions of what is essentially the same data set. So during the transformation we standardize the field definition. Maybe we'll just allow like 35 character in last name or 25 in the first name and 3 character in the rank. The exact sizes that you choose here, it may vary, but the important thing is they should be consistent in both the campuses. No matter how the source system originally stored the data, the warehouse ends up using one unified structure. The third transformation in this transformation series is deduplication, and for that let us think about the student data. Suppose both the campuses maintain separate student registration system. Campus 1 contains all these people, Sally Jackson, Richard Thompson, and Greta Williams. Campus 2 has Ted Young and Greta Williams again. Now, maybe Greta Williams is taking the courses on both campuses, so she appeared in both operational systems. But inside the data warehouse, we don't want the duplicate system record, student record, because that would completely distort, reporting and analytics. Imagine counting total student enrollments and accidentally counting the Greta twice. So during transformation, we identified duplicate entities, often using things like student IDs or social security number or Aadhaar number, email addresses, or other unique identifier. Then we merge or eliminate duplicates, so the warehouse stores only one clean master record for Greta Williams, and this entire process is called as deduplication. And this kind of transformation are again absolutely important, because without them analytics becomes unreliable very quickly. If the data is not standardized, unified, and cleaned properly, then obviously the dashboard, the report, the forecast, the business models, that machine learning models, whatever it is, and thereby the business decisions as well, built on top of that warehouse, will be inaccurate as well. So that is why it is so important. Now finally, let us continue our discussion and talk about common transformation pattern. So far we have only talked about things like data value unification, standardizing data types and sizes, and also the deduplication. Now we'll talk about some more transformation patterns that are extremely common during ETL. The first one is dropping columns, which you can think of as vertically kind of slicing the data. Imagine you're pulling the data from campus to new faculty system. We have details like first name and last name and faculty name for a few new faculty members, but then there are some other extra columns, maybe like let us say X and Y here, containing the random codes or value that really doesn't matter for analytics. So just because the source system stores that information does not mean our data warehouse needs to store them as well. If those columns are not going to help us in reporting or dashboards or business intelligence, there's no point carrying them around. So during ETL process, we simply ignore those columns. We still put in useful data like names and ranks, but we drop the unnecessary fields before storing the data in the warehouse, and that is basically called as vertical slicing, removing the certain columns while keeping the rows. Now closely related to that is something called as raw filtering or horizontally slicing the data. So for this, let us switch to a data set from the campus 1 again. Suppose we have information about 5 students. including their year and major. But imagine we are not building a university wide warehouse. Instead, we are building a data mart specifically for the College of Business. In that case, we only care about business related students and faculty. So, if some students are measuring in engineering or literature, their records are not relevant to this particular data mart. So what do we do is during ETL, we filter those rows out based on a field value. In this case, we have this major column. Only students with business related majors make it into the data mart. Notice the difference here. With column dropping, we remove the fields regardless of their values. With row filtering, we keep or remove the entire rows depending on the specific value in the data. Now, let us look at the final one, that is correcting the known error. Ideally, if there's a bad data in the source system, we would want to fix it directly here. But in reality, source system fixes can sometimes take time. Maybe the issue has already been reported, but the application team has not patched it yet. So if we already know about a recurring issue, we can temporarily correct it during ETL to keep our warehouse data clean and reliable. For example, suppose a faculty status field is supposed to store F for full time, H for half time, A for adjunct, and so on and so forth. But due to a bug in the source application, half time faculty are accidentally being stored as X or instead of H, right? So we are storing that as X. Now we already know X is incorrect. So while loading the data into warehouse, we simply replace X with H, and that way our warehouse maintains clean and standardized data even if the operational system still has that issue. And really all this transformation tie back to one major goal, that is data uniformity. When data comes from multiple systems, maybe like different campuses or different faculty applications or different student management systems, the formats and conventions are really perfectly aligned. ETL helps us standardize and clean everything so that once the data reaches the warehouse, it behaves consistently. And after that, we have achieved that consistency and cleanliness. Then comes the next big step, that is restructuring the data properly, which is where dimensional modeling and schema design start coming into the picture. Now, let us wrap our discussion on incremental ETL by looking at how all these different approaches come together in real world, kind of like a mix and match system. So at a high level, most ETL pipeline looks pretty similar. Data moves from some source system into a data warehouse, and we keep repeating that process regularly so the warehouse stays updated. But once you look under the hood, things get a little more interesting. For example, imagine we have 4 different ETL feeds connected to our data warehouse. On the surface, they all seem to be doing the same thing, that is moving the data into the warehouse. But the way each one operates can be completely different depending on the business need. Maybe 2 of those feeds update daily. Because daily refreshes are perfectly fine for that type of data. Another source system might contain highly time sensitive information, so waiting a full day would be like too slow. So in that case, we may run the ETL every hour to keep the warehouse as current as possible. And then maybe there's another dataset that barely changes at all. For something like a weekly refresh might be more than enough. So right away we can see ETL frequency is not one size fits all approach. Different datasets require different refresh schedule. Now, on top of that, remember the incremental ETL patterns that we discussed earlier. We had append and rolling append and complete replacement and in place update. Each ETL feed can use a completely different pattern as well. For instance, to feed 2 feeds might both run daily, but one could use a simple append strategy while other one perform a complete replacement every time it runs. So again, that's a important idea here. The ETL frequency and the ETL pattern, they are independent decisions. Just because two pipelines run at same interval does not mean they need to behave the same way internally. And in practice, this flexibility goes even deeper than the overall ETL feed itself. It often gets down to the individual table inside each source system. So, within a single source, one table might refresh hourly, another daily, another weekly. Similarly, one table might use append logic, another might use in place updates, while another one uses full replacement logic. So, in other words, ETL design becomes very modular. You are constantly mixing and matching refresh frequencies and loading patterns based on the nature of the data and also the business requirement behind it. And honestly, that is really the key takeaway here. There is no universal best ETL setup that works everywhere. The goal is to design an ETL process that makes sense for your specific environment, your data, your users, your reporting needs, and the speed at which the business expects information to be updated. This flexibility is what makes ETL architecture both challenging and also powerful at the same time. At this point, we have spent quite a bit of time exploring the world of ETL. So you should now have a solid understanding of the architectural side of it. We looked at different ETL patterns, different loading strategies, and a variety of transformation models that almost you will definitely encounter at some stage in a real world data warehousing project. From appends and replacements to filtering and standardization and data cleanup, we covered so many of the core building blocks that help move raw operational data into something analytics and prediction ready. Now we are ready to shift gears a little bit more. Up until now, the focus has already been on architecture, how data moves and how it gets cleaned, and how ETL pipelines are structured. From here onwards, we'll move into the design and engineering side of data warehousing, and that brings us to dimensional modeling. This is where we begin thinking carefully about how the data should actually be structured inside the data warehouse to support reporting, analytics, and business intelligence efficiently. So whenever you are ready, let us move to the next video and start talking about dimensional modeling.